Okay, this is WACE 2024. All the questions are related to probability and sampling. So all the DRVs, CRVs, and sampling. Okay, so we're starting off with calc free. Table below shows partially completed probability distribution function and a cumulative distribution function. All right, that makes sense. The probability distribution function is the probability that x takes that particular value, and the cumulative distribution function is the probability that x takes a value like up to that, okay, the probability up to that point. Okay, so first 2 marks, complete the missing probability entries in each of the tables above. So, okay, so we can start off with this. You can clearly see that these two probabilities are the same because the probability that x is less than or equal to 1 should be the same as probability that x is 1. Those two probabilities should be equal. So probability that x is less than or equal to 1 is the same as the probability that x is 1. Now, you can see the probability that x equals 2 is 0.15. So the probability that x is less than or equal to 2, if I was to show some working, there's no marks for the working out, but the probability that x is less than or equal to 2, that's what a cumulative function tells you, is the probability that x is 1 plus the probability that x is 2. We know the probability that x is 1 is 0.2, probability that x is 2 is 0.15, so this one will just be 0.2 plus 0.15, and that gives us 0.35. Okay, so therefore this probability here is 0.35. Okay, that's how it works. Then you can see the probability that x is less than or equal to 3 is 0.6. So what additional probability has come in there? The additional probability of x equals 3 has come in there. So what's the probability? What's the cumulative probability increased by? It's increased by 0.25. So effectively, this here would be 0.25. That makes sense. And then again, the cumulative probability up to 4 is 0.95. So the additional probability is the probability that x is 4. So that additional probability is effectively 0.6 plus 0.35, and that gives us 0.95. And then obviously the probability that x is less than or equal to 5 is the probability of like this, all of them added up together, which should equal 1. So therefore, that's 1. Okay, easy. So 2 marks for filling in the table, as long as you realize one was the probability up to that point, and the other one was simply the probability itself. So evaluate the probability that x is between 2 and 4. That's easy. So between 2 to 4, we just need to add up these three values. Okay, so that would be 0.15 plus 0.25 plus 0.35. Okay, and that equals 0.75. Okay, that's the easiest way of doing the question. Another way you could have done it, which I don't think is the easiest way, but another way of doing it is you could have used the cumulative function. So over here, you'll notice that we added up these three individual probabilities. We added up that, and that. Once we added those three up, we got those three probabilities. The other way you can do the probability of between 2 to 4 is you could do the probability of, effectively, we could do the probability that x is less than or equal to 4 minus the probability that x is less than or equal to 1. Okay, so that's the two ways. If I was to show even more working, again, this question's worth no marks for the working out, but over here I did the probability that x was 2 plus the probability that x was 3 plus the probability that x was 4. That's technically what I did here. I used the original probability distribution and added up those three numbers. I can use the cumulative function, and I can work out the probability that x is less than or equal to 4 minus the probability that x is less than or equal to 1. So x is less than or equal to 4 is 0.95, x is less than or equal to 1 is 0.2, and that also leaves us with 0.75. So there you go, two ways of doing that, up to you which way you pick. And the next one, probability that x equals 1, given that x is less than or equal to 3. So this is conditional probability. We want the intersection of x equals 1, and at the same time x is less than or equal to 3, divide by the probability that x is less than or equal to 3. All right, the intersection of equals to 1 and less than or equal to 3 is equals to 1. And the probability that x is less than or equal to 3 is exactly how it sounds. Okay, the probability that x equals 1, we agreed was 0.2. Well, 0.2, but same thing, 0.2. So the numerator is 0.2. And the probability that x is less than or equal to 3, we can just use the cumulative function. So x less than or equal to 3, we can use this here, which is 0.6. It's 0.2, divide by 0.6, which is 1/3. Cool. All right, question 4. 6. All right, part A. The uniform distribution continuous random variable, so this is a uniformly distributed CRV, has an expected value of 6 and a maximum value of 9. Determine the variance of x. Now, first thing first, what is a uniformly distributed continuous random variable? It pretty much means this. So it's like here to here, this is x, and all the probabilities lie somewhere between A to B. And since the width is, you can clearly see the width here is B take A. So if the width is B take A, in order for the area to be 1, the height has to be 1 on B take A. So there you go. That's what I have. And they've specifically said that for this particular question, the expected value is 6. Now, the expected value in a CRV, the expected value in a CRV is always the middle value if it's symmetrical, all right? And uniform distributions are symmetrical. So effectively, what I'm trying to tell everyone is that the expected value is 6. So 6 is the in-between value, okay? So you can think of 6 as being the in-between value. That's the middle value, the expected value, and a maximum value of 9. So B in this case is 9. So that's what I've got. And effectively, that would make A, without any working out, equal to, so remember, this is the in-between value, so A would equal 3, okay? A would equal 3. So effectively, if you didn't want to do it that way, you could have done a bit of algebra. The algebra is that the expected value is halfway between the upper boundary and the lower boundary, so A plus B divided by 2. We know the expected value of 6. Let's pretend we don't know the lower boundary. We know the upper boundary is 9 divided by 2, so that's if you wanted to show some legit working. 12 is A plus 9, again confirming that A is 3. All right, however, what does the question want? The question actually just wants the variance, okay? So what is the formula for the variance of a CRV? The formula for variance of a CRV is integral from lower boundary to upper boundary, x take away the mean squared, times by the function. That's the formula for variance. So in this case, integral from lower boundary, which is 3, upper boundary, which is 9, the expected value, which is 6, and the function, well, we know what this function is. Since the width is 6, the height is 1/6, so this here is the same as 1/6. So the function being 1/6 dx. Okay, bring the 1/6 out the front before integrating. So 1/6, and we can integrate x take 6 squared very easily because the derivative of the power is 1. So this just becomes x takes 6 to the power of 3 all over 3 from 3 to 9. Okay, great. I'll bring the 3 out the front as well, so that's 1 on 18. And then x takes 6 cubed is really all that we're putting through the boundaries from 3 to 9. So what does that yield? All right, 1 on 18. 9 takes 6 is 3, so 3 cubed. 3 takes 6 is negative 3 cubed. So that's 1 on 18. And then 3 cubed is 27. Take 27 is another 27. 27 plus 27 is 54. So 54 divided by 18, which is 3. There you go. That's the variance. Now, I'm not sure if you're allowed to use this formula, but it's a good way to double check. I know that for a CRV, I know that for a uniform CRV, obviously the formula for expected value I just discussed. The formula for expected value for a uniform CRV is A plus B divided by 2. The formula for variance, which is something that I've memorized, you can actually prove it. It is B take A squared on 12. That is the formula for variance. You can't just use it straight away, but it's a good way to double check your answer. So if I did want to double check my answer and use that formula for variance, so in this particular case, the B was 9, A was 3 squared divided by 12. 9 take 3 is 6. 6 squared is 36. 36 divided by 12 is 3. There you go, confirming that I did get a variance of 3. So it's a good way to double check your answer, but I don't think you're allowed to just use that formula straight away. You're allowed to use this formula because that shows that the expected value is in the middle because it's symmetrical, but you just can't use the variance formula straight away. Okay, the binomially distributed DRVW has a mean of half and a variance of 5 on 12. Evaluate the probability that W is 1. Okay, It's a binomial with a mean of a half. So the formula for mean is NP. So effectively NP is half. And the variance of 5/12. So that's NP. 1 take P is 5/12. Cool. And we have to evaluate the probability that W is 1. Okay, so according to the binomial formula, the probability that W will be 1 is, well, what is the binomial formula? Does everyone remember the binomial formula? If you had to do it manually, because this is calc-free, if x follows a binomial distribution with those parameters, the probability that x takes any particular value is p to the power of x, 1 take p to the power of n take x, and then n choose x. That's the formula for binomial. So if you want the probability that W is 1, that would be whatever the probability is to the power of 1 times 1 take away the probability to the power of, we don't know what n is, so n take 1, and then n choose 1. Alrighty, and anything choose 1, for those that have forgotten, anything choose 1 is always n. Just like anything choose 0, which is the same as anything choose n, which is 1, you should really know that anything choose 1 is just n. So anyway, we want the probability that W is 1, but we don't know what n is and we don't know what p is. That's why they've given us this information so that we can work out n and we can work out p. So the best way to do it, the best way to do it, is we know that NP is half, right? So instead of writing NP, I can just replace NP with half. So what I have is half, and then 1 take P is 5/12. See how easy that is? That's so easy way to figure out what. I'll times both sides by 2, so this becomes 5/6. So 1 take P is 5/6, which means P is 1/6. So there you go. We now have P is 1/6 to the power of 1, obviously. 1 take P, which is 5/6 to the power of n take 1. So now I just have to work out what n is. Okay, so to work out n, I know P is 1/6. I can just chuck it back into this formula. NP is half. We just worked out P is 1/6. So n times by 1/6 is half. Half divided by a sixth is 3. Number of trials is 3. So then this over here would be 2. And this here would be 3 choose 1, which we agreed was just 3. Anything choose 1 is itself. So what does that yield us an answer of? So we have 1/6, and then 5/6 squared is like 25 over 36, and then times by 3. Okay, cool. So had to be good with your algebra. The 3 and that could become a 12, and then we're pretty good. So effectively, final answer is 25 over 72 is the probability that W is 1. So there you go, binomial without a class pad. Okay, so that's all the probability that was in the calc free. Let's do the calc assumed, which will have all the sampling as well. All right, a maths teacher uses a coin flip actively to demonstrate confidence intervals to their class. They flip a fair coin 50 times, they get 30 heads and 20 tails. Cool. Calculate a 90% confidence interval for the proportion of heads obtained. Okay, now it's only worth 2 marks, and if it's only worth 2 marks, you can put that straight in the class pad. There is no marks for the working out. As long as everyone recognizes that the sample proportion, I usually prefer this, the sample proportion is of tails, so proportion of heads. So the proportion of heads is 30 over 50, which is 0.6. So, all right, I mean, remember, it's worth no marks for the working out, but if you did want to, what's the formula for confidence intervals? The population proportion is pi cap plus k lots of the standard deviation, which is pi cap, 1 take pi cap all over n. So that's the upper boundary of the confidence interval, and the lower boundary of the confidence interval is the same thing, but minus away the k lots of the standard deviation. Cool. So in this particular case, what we would be doing is 0.6, take k, 90%. We know the k value for 90% is 1.645. So 1.645. Lots of pi cap, which is 0.6 times 0.4, all over the number of trials, which was 50 trials, is less than this, is less than, and then we chuck it over here. Okay, except the second time around, it will be plus. Put that straight into your class pad, and to 4 decimal places, we'll get a 90% confidence interval of 0.4860. is less than pi is less than 0.7140. Okay. Sometimes I see them a bit lazy. They just write it like this. Sometimes they just write down confidence interval is, and I've seen them just write down 0.6 plus or minus the standard, or 1.645 lots of the standard deviation. So sometimes if they're really lazy, they just write this, and then they write it like this, and they write 0.4860 comma 0.7140. Okay, but it is safe to put it like this. Now, whether you write less than or equal to, it makes no difference. Yeah, it really makes no difference. You could have put equals to here if you wanted to, equals to. It's a CRV, so it makes no real difference. All right. How would you have done that on your class pad for the 2 marks? You could have easily done it on your class pad for 2 marks. All you got to write down is, you go into stats. So we go to stats, we go calc, interval. We want to change it to 1 prop z int. Press next. Press the help button if you want. It tells you exactly what to sub in. So the confidence level as a decimal is 0.9. X is the number of heads, which is 30. N is the number of trials, which is 50. Press next, and there you go. You get those numbers, 0.4860 and 0.7140. Okay, that's if you wanted to use your class pad. All right, as a homework exercise, the teacher asks all 20 students to repeat the coin activity. Alrighty, and calculate their own 90% confidence interval for the proportion of heads. Alrighty, so, great. Let x be a random variable that denotes the number of students whose confidence interval contains a true proportion of heads. All right, nice. So guys, do you realize that x is a binomial? How do I know that x is a binomial? I know that x is a binomial because either the confidence interval does contain the true proportion or it does not contain the true proportion. And we know that there's a 90% chance of it containing the true proportion. So really, x is a discrete random variable. Specifically, it's a binomial distribution. It's a binomial distribution with 20 trials, and the probability that any particular confidence interval contains a true proportion of heads is 0.9. Since it's a 90% confidence interval, the proportion is 0.9. Alrighty, so that's it. That's the distribution. And then they want the expected value and variance. Well, what's the formula for the expected value of a binomial? Formula for expected value of a binomial is NP. So 20 times 0.9. So we expect 18. And variance is NP, 1 take P. So that would be 20 times 0.9 times 0.1. And that gives us 1.8. Part D. What's the probability that the confidence intervals of 3 students do not contain the true proportion? Alrighty, 3 students do not contain the true proportion. So if 3 students don't contain the true proportion, that means 17 students do. So effectively, we simply want the probability that x is 17. So this goes straight into our class pad. We know it's a binomial distribution. It's clearly a binomial distribution for the number of samples that contain the true proportion. Distribution, continuous, norm, PDF. We want 17. We know that the standard deviation was, whoops, why am I in norm? It's distribution, discrete, binomial PDF, that's what I meant. We know we want 17 trials, number of trials 20, and the probability of success is 0.9. 90% confidence intervals have a 0.9 probability of containing the true proportion. All right, that gives you 0.1901. 0.1901. Cool. A book called Why I Love Mathematics is having its first print run. This is scheduled to last for 1 week using 4 printing presses. The publisher claims that historically, 10 books have printing errors for every 200 that are printed. Okay, 10 books for every 200 that are printed. Okay, so what's that a proportion of? That's a proportion of 10 out of 200. I don't know if I'm going to need that number or not, but I'll just write that down. So this, since it says historically, that sounds like a population proportion. So the population proportion of books with printing errors is 10 over 200, which I guess simplifies out to 0.05. I might need that. A sample of 200 books is to be chosen to determine how many contain errors. The proposed sampling procedure is to select the first 200 books over a 6-hour window using the nearest printing press. Okay, so you can see that that's just riddled with all sorts of bias. So, I mean, where's all the bias? If I was to highlight all the bias, one, they're just going to select the first 200. What if like the printing press what if the printer gets like worse over time, it wears out over time, blah blah blah. So or what if the first few are rusty before the machine warms up and then it starts to get better. So that's the issue, is that only the first 200 books over a 6-hour time period window. All right, and not just that. So limited time period, just 200 books only. And not just that, they're only going to use the nearest printing press. Surely we should be looking at all the printing presses and selecting them randomly from all the printing presses and not just the newest printing press. So, alrighty. Blah, blah, blah. Okay, so there you go. That's its issues. So explain one source of bias. How many presses are there? We are blah, blah, blah. The schedule to last. There you go. We're even told that there's 4 printing presses. We're even told that there are 4 printing presses. They want to know, we know that we're trying to figure out the proportion of errors in 4 printing presses. So just using the nearest printing press is not good enough. Okay, so effectively identify and explain one possible source. Oh, you only had to discuss one source of bias. So one source of bias could have included the fact that the sample only includes books from the nearest printing press, includes books from the nearest printing press. All right, and then we have to explain, so we can say which may perform differently, to the other 3 presses. So that's the first issue. Second issue was the sample was gathered over a very narrow period of time, only the first 20 books. So sample was gathered by selecting the first 200 books in a narrow time interval, in a single narrow time interval. Alrighty, and remember, at the end of the day, we are looking at, specifically, we're trying to figure out what happens over a period of 1 week. We're trying to figure out what happens over a period of an entire 1 week period. Okay, so we can't just look at the first 6 hours. So that will help me explain. So we can explain that. So books printed later in the week. So books printed later in the week are not included. And what's going to be the problem with later in the week? So different operators, there'll be different operators over time, different operators and performance of the press, etc. Different operators and performance of the press. Different operators and performance. What have I said? So books printed later in the week, where there's different operators and performances of the press may vary. So books printed later in the week are not included. Perfect. I had to explain that extra description because it says explain the source of bias. Remember, bias, the definition of bias is when a sample is not reflective. Sample is not reflective of the population. If a sample is not reflective of the population, it introduces bias. So if you are only looking at the first 20 books in that first 6-hour window, the books printed later in the week when there's different operators or the printing press may perform differently are not included, and that's clearly a source of bias. Identify two changes to the sampling procedure that would reduce the bias. Well, we addressed the two things. So first of all, the sample should randomly select books. We could say from books printed throughout the week. So from books printed at any time during the week. And not just that, add books printed from all printing presses. From all 4 printing presses. So with all these questions on sampling and bias, I highly am reflective of the text, okay, or the information they give us. So one of them was we had to reflect that we're going to look at any time during the entire week and from all four printing presses. There you go, as per the question. If we're trying to figure out the proportion of books that have errors across an entire week across 4 printing presses, then really we should be selecting our sample from all of that. All right, let's assume the sample was gathered using this improved procedure. Fine. Alrighty, and that the publisher's claim is correct. Well, what's the publisher's claim? The publisher's claim is that the population proportion is 0.05. Use the approximate normality of the distribution of sample proportions. I love that phrase. The approximate normality of the distribution of sample proportions. Because what I mean, if they don't use the word approximate, we all know that the sample proportion per se, with the sample proportion, strictly speaking, follows a binomial distribution where the number of trials is like n, whatever it is, and the probability is, well, whatever the probability is of a dodgy book. So in this particular case, ideally, the sample proportion follows a binomial distribution where the number of trials is, I shouldn't say sample proportion, well, I guess the number of books that have printing errors follows a binomial distribution, and this binomial distribution has got 20, how much trials does it have? 200 trials? 200 trials, and the probability of an error is 0.05. That's the exact distribution, okay? This here represents the exact distribution of the, this is the exact distribution of the proportion of books with a error. But remember, we can approximate this exact distribution using a binomial, okay? Using a normal. That's why they said the approximate normality. So the phrase the approximate normality means that this gives you the exact distribution of the number of books with errors, exact distribution of number of books with errors. Whereas if I was to use a normal distribution, then it would be the sample proportion follows a normal distribution where the number of trials is again 200, but we all know the formula for standard deviation. So the formula for standard deviation would have been root 0.05 times 1 take away that, so that's 0.95 all over n, which is 200, and then variance squared. And this, guys, gives you the approximate distribution. All right, it gives you the approximate distribution according to central limit theorem. It gives you the approximate distribution of the proportion of books with errors, specifically the sample proportion of books with errors, but same thing. Cool. So that's what I like the phrase approximate normality. So the fact that they use the fact approximate normality and sample proportions is why I had to use a normal distribution. If they did not use those phrases and they just said like proportion of books with an error less than 0.04, then the exact distribution would have been given by a by a binomial, but because it said approximate normality of sample proportions, that's why we're going to do a normal distribution. So in this case, exactly what I just wrote, we'll just copy paste that. So the sample proportion of books with errors is a normal distribution with these parameters, and we want the probability that the sample proportions is less than 0.04. All right, so we want the probability that the sample proportion will be less than 0.04. Okay, and that goes straight into my ClassPad into normal distribution. So interactive, continuous norm CDF. All right, lower boundary, technically negative infinity, which I know it makes no sense. How can a proportion be below 0? But we just write down negative infinity. Upper boundary is root, and then we had 0.05 times 0.95 divided by 200. Whoops, that's the standard deviation. Sorry, that's the standard deviation, which goes, whatever. Upper boundary is 0.04, and standard deviation is what I just said before. So root 0.05 times 0.95 divide by 200. Cool. And the mean value is 0.05. Okay, cool. And we get a probability of 0.2582. Easy. 0.2582. If I wanted the exact probability, I would have actually done this. If I wanted the exact probability, I would have said, this is again not what they want us to do, but if I wanted the exact probability, I would have said X follows a binomial distribution with 200 trials. Probability is 0.05, just like I did earlier. And then I would have done probability that X is, okay, so if you want a sample proportion less than 0.04, okay, so 0.04, what is 0.04 of 200? 0.04 of 200 is 4% of 200. 4% of 200 is 8. So they want the probability that X is less than 8. So then effectively that means 0 to 7. So we want the probability that somewhere between 0 to 7 books have got errors in them. So then what I'll do, interactive, distribution, discrete, binomial CDF, lower boundary 0, upper boundary 7, number of trials 200, and probability of success is 0.05. And that should give us a similar probability. There you go, 0.2133. This is the exact probability, okay? You'll notice, guys, the reason why it's a little bit off is because we made a lower boundary 7. So had I kept my upper boundary 8, you would have seen that we get a number slightly bigger. Average these two numbers, this plus this, and then divide it by 2, and that should get you very, very, very close to what the approximate normality was. That number there, which is very close to the actual answer that we got, which was 0.258, okay? 0.258, 0.270, they're like almost the same. It's like a 1% off-ish, okay? So there you go. That's one of the hardest parts about sampling. One of the hardest parts about sampling is when do you do normal distribution, when do you do binomial distribution. You do binomial distribution if they don't use the word approximate and they don't use the phrase sample proportions. Okay, the binomial distribution will give you the exact distribution of number of books with errors. Notice it will tell you the number of books with errors, whereas a normal distribution will give you the approximate distribution of the sample proportion of books with errors. Okay, cool. In a different sample of 600 books, it was found that the proportion of books containing an error is 0.1 with a margin of error of 0.024. With a margin of error of 0.024. Determine a 95% confidence interval that will have printing errors. Okay, well, do you guys realize that they've straight away given you the margin of error? All right, it's a unique question where they've just straight up given you the margin of error straight away. So if they give you the margin of error straight away, the confidence interval is easy. The confidence interval for the population proportion is blah, 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 0.1 plus 0.024 and 0.1 take 0.024. Okay, that's exactly what it would be. Or you could have written it like this, depending on the teacher. The confidence interval, so some teachers are pretty okay with this, is the sample proportion of 0.1 plus or minus. Instead of writing, I hope everyone realizes that the margin of error, that margin of error is referring to k lots of root pi cap 1 take pi cap over n. So that's why we don't have to bother doing all of that, because it tells us that the error straight away is that straight away. They tell us that straight away. You know what would have been better? It would have been better if they at least told us that this margin of error corresponds to a 95% confidence interval, but anyway, we know what they meant. So the final answer for the confidence interval is 0.0760 to 0.1240, okay? Or if some schools are okay with you writing it in a set of brackets. So 0.0760 to 1.024, they're also okay with that, okay? On the basis of the confidence intervals in part C, is the proportion of books with printing error different to what was claimed by the publisher? Alrighty. Well, what was the confidence interval? Did we create? Okay, so the publishers claimed that the proportion of errors, the population proportions, was 0.05. Okay, so we can explain that they claim that. Now, is 0.05 lie within here? No, it does not. So we can explain that. First of all, we can say that the publishers claimed a population proportion of 0.05. Okay, population claimed a population proportion of 0.05, i.e. proportion of books with errors. So this proportion is not within the 95% confidence interval. So this proportion is not within the confidence interval, and hence there is sufficient evidence. Hence there is sufficient evidence at the 95% confidence level. It's important you mention which confidence level you have this evidence for. So there is sufficient evidence at the 95% confidence level that the publisher's claim is incorrect. The publisher's claim is incorrect or is false. Okay, easy. So just two changes that could be made in order to decrease the margin of error. All right, two changes. Okay, well, we just discussed the formula for margin of error. The formula for margin of error was this. This was the formula for margin of error. So you can clearly see that there are, a few things that affect the margin of error. K affects the margin of error, N affects the margin of error, and the actual proportion itself affects the margin of error. The closer the proportion is to 0.5, the greater the margin of error. So pretty much the two changes that could be made, well, you really can't change the proportion. That's not up to us to change the... Think about it. The proportion is the one thing that you have no control over. The proportion is what it is. So what I'm trying to say is that even though the sample proportion itself does affect the margin of error, it's not something that we can change. We can't change the sample proportion. It is what it is. What we can change is we can write that the error is directly proportional to K. Therefore, one thing that we could do is decrease the confidence level. Remember, we're trying to decrease the margin of error, so therefore decrease the confidence level. E.g. a 90% confidence interval instead of a 95% confidence interval, 90% confidence interval. That's one of the things that we could do. And the other thing you can see is that the error is inversely proportional to the square root of the sample size. Okay, the error is inversely proportional to square root of sample size. So something else that we could do is therefore increase the number of, or basically increase the size of the sample. Increase the size of, that's a foolproof way to achieve that. Okay. Determine the minimum sampling size that would be necessary to guarantee that the margin of error was at most 0.02. Now, few keywords there. Keywords being, the keywords in this case, minimal sample size, that's keyword, and another keyword being guarantee that the margin of error is less than something something. So all those things imply worst case scenario. So we have to, like the marking key even says, consider worst case scenario, consider a worst case scenario of a proportion, worst case scenario set of a population proportion equal to 0.5. So here's the thing. If any question says find the minimum sample size and they don't use the phrase assuming the sample proportion is correct. If they don't use the phrase assume the sample proportion is correct, we have to consider a worst case scenario of a sample proportion of 0.5. Okay? We have to use 0.5. If they just said determine the sample size and they said, well, even if they didn't say minimum, if they have to use the phrase assuming that this sample proportion, that sample proportion or whatever sample proportion is correct. So we're going to do worst case scenario because we have to guarantee that the error is at most 0.02. So if we want the error to be less than 0.02 at the 95%, so we have to do k lots of root pi cap 1 take pi cap all over n has to be less than 0.02. So k is 1.96. Worst case scenario, pi cap is 0.5. This is what I was trying to tell you, that even the sample proportion affects the width of the interval. That even affects the error itself. So 0.5 times 1, take away that, divide by n, has to be less than 0.02. Alrighty, and then you always round up for this. Okay, always round up. So what do we have? In fact, I'll prove that you round up. You just sub it in as an inequality. So 0.02 is, the error has to be, what did I say? The error has to be less than 0.02. So I'll write it at the front. Square root, worst case scenario is 0.5. We're trying to figure out the sample size, and this has to be less than 0.02. This will show you that you have to round up. So like I said, I told you that you always round up for like finding out the minimum sample size. This will prove that we do. So blah, blah, blah. It helps if I write the 1.96 at the start. 1.96. Cool. We get x is more than 2401. So at most 0.02 means less than or equal to 0.02. So n is greater than or equal to 2401. So determine, therefore, minimum sample size of 2,401. Cool. A protest group looking to abolish the circulation of physical money claims that 74% of Perth residents have not used physical money in the past 12 months. To investigate this claim, a data scientist surveys a random sample, and he found 70% have not used physical money. Now, so, okay, fair enough. So he does a random sample. Sure, so if he does a random sample, the 70% is a sample proportion. Let P denote the proportion of Perth residents who have not used physical money in the past 12 months. Given that the width of the 95% confidence interval is this, determine the 95% confidence interval for P. Okay, well, pretty easy. Think about it. They've specifically told us that the width is this. Alrighty, the width of the confidence interval is 0.096. Now, I hope everyone realizes that the width is double the error. Okay, so the error is just the width divided by 2. The error is the width divided by 2, so the width is 0.096 divided by 2. 0.096 divided by 2 is 0.48. So we have a margin of error of 0.048. Great. So if we know that, and we know that the sample proportion is 0.7. The sample proportion is 0.7. This topic is all about trying to read behind the English. So we can't use the 74%. That's just what some protest group claims. We can only create a confidence interval based on a random sample. So we did have a random sample. A data scientist got a random sample. He found a sample proportion of 0.7, but he knows that there is a margin of error. So that's why he created a confidence interval. The width of the confidence interval was 0.096, which meant that the error was 0.048. And really, we now know that the confidence interval is somewhat for like P is somewhere between 0.7 plus 0.048 and 0.7 minus 0.048. Simple as that. Alrighty, so 0.7 take away that is 0.652. And then the upper boundary is 0.748. Easy. How many people were surveyed? Determine the number of people surveyed. Well, that's easy. We know that the error, so here's the thing. We know that the error is 0.048. We know that the error is 0.048. And the formula for error, we've discussed a couple of times now. Error is confidence level times this, the standard deviation, pi cap, 1 take pi cap, all over n. Now, we just worked out the error to be 0.048. So if you worked out the error to be 0.048 equals k, which was 1.96, root pi cap, which we were told were 0.7, times 0.3, all over the sample size. And you just put that straight into your class pad and solve it. Well, you get 350.14, but you can't have a decimal number of sample size, so therefore we just round to the nearest number. For something like this, you just round to the nearest number. It didn't say find the minimum number of people, it just said find the number of people surveyed. This is a very, very, very common question, okay? There was another way of doing it. This was the quickest way of doing it, but there was another way of doing it. You could have done simultaneous equations. We know that the lower boundary is 0.652, so what we could have done is we could have written, let's pretend we didn't even know. So what I'm trying to tell you is I am able to use just the confidence interval. I'm able to use just the confidence interval to work out both the sample proportion as well as the sample proportion as well as the number of people surveyed in the sample. So this is the lower boundary, right? So the lower boundary is 0.652. So what I'm trying to say is we could have written this 0.652 is the sample proportion. Now I know it's 0.7, but I'm going to pretend I don't know it. Take away 1.96 square root of pi cap, which I'm pretending that I don't know. 1 take pi cap all over n. That's the lower boundary. And the upper boundary is 0.748. The upper boundary is 0.748, and the upper boundary is the sample proportion plus the margin of error, so plus 1.96 standard deviations. And then you can just put that into simultaneous. You can put that into simultaneous. Obviously, it's a bit more effort, especially because we get given the sample proportion, but still doable. So one equation was what was my lower boundary? 0.652 equals 1.96 times x times 1 take x divide by y. So that's one equation. And then the upper boundary, so the lower boundary had been 0.652. The upper boundary had been 0.748. And, whoops, this was meant to say x plus this, take this amount. And this was meant to be x plus this amount, x comma y. If you do that, we get 0.7 and 350.1415, like I said earlier. Okay, so there you go, two different ways of doing that question. Alrighty, what does the data scientist confidence interval suggest about the protest group? Now, the data scientist says a sample proportion between 0.65 and 0.75. Well, 74% is 0.74, which is within that confidence interval. Okay, so we can explain that the sample proportion, all right, so the proportion of 0.74 claimed by the protesters does lie within the 95%, does lie within the 95% confidence interval. It does lie within the 95% confidence interval. So what does that mean? Just like I said, so exact same words as before. Previously I said that there wasn't sufficient evidence. This time I will say that hence there is sufficient evidence. Hence there is sufficient evidence that the protesters' claims are true. It's as easy as that. Hence, there is sufficient evidence at the 95% confidence interval that the protesters' claims, claim is true. Easy. Simple as that. All right. What does yep suggest? Yep, so it concludes that cool. Great. Great. The data scientist is interested whether the proportion is similar to that in other Australian capital cities. So he does surveys in Brisbane, Sydney, and Hobart. Well, which one was this? This one was in Perth. Okay, so he does simple ones. All right, he's got various different sample sizes with various sample proportions. For each of these, we have to figure out which one will have the widest confidence interval. So I'm glad this question came up. What two things affect the confidence interval? And now don't forget, guys, the confidence interval, the width of the confidence interval is 2 errors. So when it says which of these affects the width of the confidence interval, it effectively means which of these affects the errors. So between Brisbane and Sydney. Now between Brisbane and Sydney, you can see that they've got the same sample proportion, but various sample sizes. So as we discussed earlier, since the width is 2 errors, we did discuss earlier how the error was proportional to 1 divided by square root of sample size. And since error equals 2 width, the width is also proportional to square root of sample size. So therefore, you can clearly, as Sydney has a larger sample size, we want which one? We want the widest. Okay, we want the widest confidence interval, which means we want the biggest error. So biggest error, if you want the error to be big, you want n to be small. So therefore, n is small in Brisbane. Therefore, Brisbane has a wider confidence interval due to its smaller sample size. Due to smaller sample size, and obviously same sample proportion, which is not really important, but just trying to confirm that all the other things were uniform. It has the same sample proportion. Now, here's the important thing. What about between Brisbane and Hobart? Now, Brisbane and Hobart, they both ask n people. Sample size is the same. What's different is the sample proportion. Alrighty, so guys, the error is also, error slash width. So I'll write error first. The error is directly proportional to pi cap 1 take pi cap. It is, or square root of pi cap 1 take pi cap. The error is directly proportional to that. So the width is also directly proportional to that. So here's the thing. we know the closer it is to 0.5, the closer that these individual proportion and the closer that the proportion and one take proportion is to 0.5, the larger the error and larger the width. So, and I can prove that to you. So Brisbane's 0.65, Hobart's 0.75. So if I had to prove it for you, the width in Brisbane is proportional to 0.65 times 0.35, whereas the width in Brisbane versus Hobart is proportional to 0.75 times 0.25. Now, so for those that didn't know that 0.5 is the worst case scenario, if you did not know that 0.5 is the worst case scenario, then you'd have to do these calculations. But since 0.5 is the worst case scenario, this 0.65 is much closer to 0.5 than this. These two values are much closer to 0.5 than these two here. So I'm confident that this here will give me a bigger error, okay? And you can do it on your calculator. So if I do square root of 0.5 times 0.5, let's just say sample size 1, doesn't really matter. We get half. So as a decimal, we get, actually we didn't have half. What do we have? 0.65 times 0.35. That was one of them, which as a decimal was 0.47. And if we change that to 0.75.25, look what it does. If I change that to 0.75.25, it becomes this number, which is 0.43. You can see it's not as bad as 0.48. Okay, it's not as bad as 0.48. And by the way, you can see the worst was 0.5. The worst was 0.5. If I do 0.5, we literally have the biggest possible number there, which is 0.5. So what I'm trying to tell people is the closer it is to 0.5, the bigger the error, the bigger the margin of error, and the larger the sample size you need to guarantee a certain error. So effectively, I've written enough working out, and then we'd explain that therefore Brisbane again has a wider confidence interval. Therefore Brisbane again has a wider confidence interval. Brisbane has, due to, and in this case it's not due to a smaller sample size, due to sample proportion closer to, sample proportion closer to 0.5. Closer to 0.5. And obviously, and same sample size. So the sample size was not the deciding factor, it was the confidence in the sample proportion itself. And that's what I was trying to tell you earlier, that the error is affected by three things. The error is affected by the sample proportion, which you can't really change unless in the question itself we have different sample proportions. Brisbane has a sample proportion of 0.65 and Hobart has a sample proportion of 0.75. Those are not things that I changed. They were what they were. The sample size and then the confidence level itself. Okay, cool. They all had the same confidence level because they were all 95%. Okay, so good question. Alrighty, number 13. Brianna is considering buying an electric vehicle from Zephyr Motors. The manufacturer claims that on average, a driver will be able to drive 350 kilometers before needing to recharge the vehicle. And the probability of traveling more than 400 kilometers is this. Fine. I don't know what type of distribution it is yet. Has it said normal distribution? Blah, blah, blah. Yes, it does. It says assume that X is a normally distributed random variable. Okay, so 2 marks, determine the standard deviation of X. Okay, so fair enough. Now, ideally, I mean, look, it's only 2 marks. If it's only 2 marks, you literally just get mark for the answer. So if it was worth 3 marks, look what I would do. So I'll show you the difference between a 2 mark working out and a 3 mark working out. So this is a 3 mark working out. It's quite a bit of effort, but this is a 3 mark working out. So first, just so that everyone can visualize it, there's no marks for the picture, okay? The picture is just to help students visualize. So we have some normal distribution that looks like this. X is your actual score. X is the actual number of kilometers traveled. X is the actual number of kilometers traveled. And since the standard deviation is missing, do you guys realize that they don't tell you the standard deviation? So we use z-scores. We know the mean. We know the mean is, on average, driver will be able to travel 350 kilometers. So the mean is 350. Standard deviation is unknown. But then we do a z-score. So if we do a z-score, the mean is 0 and the standard deviation is 1. And we know that the probability of traveling more than 400 kilometers before needing recharging is 0.2525. So 400 is somewhere over here, and then the corresponding probability here is 0.2525. Cool. So if I do z-scores, we replicate this right here. We call this k. We replicate the probability of 0.2525. This is if it was worth 3 or 4 marks where you have to show working. So here would be my working. Z follows a normal distribution, mean of 0, standard deviation of 1. First, I'll find out the probability that Z is more than K is 0.2525. That will give me a z-score. Alrighty, so let's see what z-score I get. Interactive, distribution, inverse, and we're going to do inverse norm CDF. Alright, we do inverse norm CDF. Probability is to the right. Probability is what is our probability? The probability was 0.2525. 0.2525. Standard deviation was 1 and 0. Yep, because it's z-scores, we get 0.6666. 0.6666. And then we know the formula for z-score. Z-score is actual score, take mean, divide by standard deviation. Remember, the picture is no marks. This is what the marks were for. So the z-score is 0.6666. The actual score was 400. Remember, K was the z-score. 400 was the corresponding actual score. Okay, so again, if I highlight that for you, K was your z-score, whereas 400 was your actual score. Okay, so 400 was your actual score. So we sub those specific numbers in. Mean we know to be 350, and we don't know what standard deviation is. Put that into the calculator and we get a standard deviation of, let's have a look, should be close to about 75. So this equals fraction 400, take 350, divide by x, and we solve that. And we get, yep, 75. Okay, so to the nearest, even to 2 decimal places, it's 75.00. All right, standard deviation is 75.00 kilometers. Now, it's interesting, guys. It's worth 2 marks, which means no working out needed. But if you look at the SCARSA marking key, they say 1 mark for the z-score and 1 mark for then calculating the standard deviation. So that's interesting. Even though it's a 2 marker, and really it should be 2 marks for the answer, it does allocate 1 mark for the z-score and 1 mark for that. So maybe just safe. This is just maybe just safe to do it using z-scores. Now, having said that, technically it's only worth 2 marks. So technically you could have just done this. Really, you could have just done z squiggly norm. Sorry, not z, x. X follows a normal distribution with a mean of 350, a standard deviation which is unknown. So we can just write that. And we could just write down probability that x is more than 400 is 0.2525. And you know what? Solver can handle it. Solver can handle it just fine. So what should I do? Interactive, distribution, continuous, norm CDF, lower boundary. So 400, upper boundary is technically infinity. Standard deviation, I'm going to write down x, mean 350. All right, it will say error, whatnot, that doesn't matter. So we want this probability to be 0.2525. And then we just solve it. Alrighty, and there you go. You get the exact same answer. So solver can handle it as well. If mean is missing or standard deviation is missing, solver can handle it. But I'm not sure if you're going to get full marks or not, okay? But you get the same value, a mean of 75.00 kilometers. All right, Brianna will need to travel regularly to Albany, which is 420 kilometers from her house. Calculate the probability that on any given day, she'll be able to drive to Albany without recharging the vehicle? Okay, well, it's highly unlikely, right? Because we know the mean is only 350. The mean is just 350. So it's highly, highly unlikely. So x squiggly norm, mean is 350. Standard deviation we just worked out to be 75. And we want the probability that x is more than 420. This is going to be highly unlikely. Interactive, distribution, continuous, norm CDF. Continuous norm CDF. We want the probability that her car will go for more than 420 kilometers. I don't think it's likely at all. It's well above the mean. Standard deviation is 75. Mean was 350. Probability is 0.1753, so quite unlikely. There's a low chance that her car can go. Think about it, the average is 350, so if she wants to travel like 420 kilometers, we already know that traveling more than 400 kilometers has a likelihood of 0.25 only. So traveling like even more, traveling 420 kilometers should have a probability even less than 0.2525. Alrighty, so there you go, 1 mark, just straight for the answer. Matthew is interested in buying the same type of electric vehicle, but he lives in England. He wants the distances in miles. Alrighty. Okay, so it's like a change of scale, change of origin question. Let y, okay, 1 mile is 1.6 kilometers. Now be very, very careful. Miles is less than kilometers. Remember that? Miles is less than kilometers. So let y be the random variable that denotes the distance in miles. Determine the expected value and variance for y. So here's the thing. Alrighty, so when I first did this, I know this is what I did, and this was wrong actually, okay? So can I just show you what I did when I first did this question in WACE? I actually did it wrong, and then I realized immediately I did it wrong. So what I did in WACE is I wrote down that y is 1.6x. I just thought, yep, 1 mile is 1.6 kilometers. Therefore, the distance in kilometers is x's, the distance in miles is y. So I wrote this down, and then the first thing that I wrote in WACE is that I wrote down, well, the expected value of y is 1.6 times by the expected value of x. So then that's 1.6 times by the previous expected value, which was 350, and 1.6 times 350 gives you, well, whatever it gives you. So 1.6 times 350. 1.6 times 350, and look what it gives us. It gives us 560. It gives us 560. And as soon as I wrote that, I was thinking that how is that possible? How is it possible that the expected value is 350 kilometers, but at the same time 560 miles? That's like even more, all right? 560 miles is like a big, big, big distance. And that's what I realized, that I've done this all wrong. This has been done incorrectly. So what is the correct way of doing it? The correct way of doing it is realizing that yes, 1 mile is 1.6 kilometers, and what that really, really means is that if 1 mile is 1.6 kilometers, what that really means is this. It means that y is x divide 1.6. Think about it. If you want to go from miles to kilometers to miles, you need to divide by 1.6. If you divide the kilometers by 1.6, the number becomes smaller. If the number becomes smaller, then that will turn it into miles. So really another way of writing this is like 1 on 1.6 x. Another way of writing this is 1 on 1.6 x. Perfect. And now, knowing that, it's actually much easier, and now I'll get the correct answer. So the expected value of y is 1 on 1.6 times by the expected value of x. So 1 on 1.6, the expected value of x was 350. And if you do 1 on 1.6 times 350, you will get the correct answer. You'll get the 218.75 miles. Important that we write the units down. This one is correct. And now the variance, we all know that the variance is affected by this thing here squared. So it's like 1 on 1.6 squared times by the old variance. So 1 on 1.6 squared. And what did the old variance used to be? Well, the old standard deviation used to be 75. So times by 75. squared. And that gives you 2197. And then don't forget to write miles squared, because that's technically what it is, miles squared. Cool. And that's the expected value and variance of y. All right, Brianna decides to consider an electric vehicle from a rival company, Spruky Cars. And there's the histogram below. Let W be a random variable that denotes the distance that a Spruky car vehicle will travel before needing to recharge. There you go. You can see there's W, blah, blah, blah. On the basis of the histogram, is it appropriate to use a normal distribution to model this? Now, guys, you can clearly see that this is skewed to the left, okay? There's a clear skew to the left. So it is not suitable to use a normal distribution. We can explain no. Normal distribution is not suitable. Distribution is not suitable as the graph is skewed to the left. You didn't have to just write skewed to the left. You didn't even have to write skewed. You could have just said it's not symmetrical, okay? You could have said it's asymmetrical, all right? And that would have been sufficient, but I'm just going to say skewed to the left. So, assuming the distances are uniformly distributed within each interval, what does that even mean? It just says that you can see how there's what? There's like, there are 4 people between 260 and 280. So we just got to assume that the 4 people there are like equally spread. So like one's at 260, one's at 265, one's at 270, one's at 275, etc. We assume everyone is like just uniformly spread within that interval. So anyway, we have to estimate the expected distance that a Spruky car will be able to travel. Now, estimate, the reason why it's an estimate, the reason specifically why it is an estimate is because we're assuming the distances are uniformly distributed within each interval. So honestly, it's a lot of work for 2 marks. Okay, I was surprised that they even asked this. A lot of work for 2 marks. So the expected distance. Now, guys, it's almost like a DRV. It almost becomes a DRV. So you have to just assume you just use the midpoint of each one. So this one, guys, is 270. This is the midpoint of that one. This one's got a midpoint of 290. This one's got a midpoint of 310, 330, 350, 370, 390, 410, 430. So we're going to assume that if everyone's equally spread, you might as well just assume that everyone within this section, within this block, within this interval, that everyone's traveling at 270, which is the halfway mark. You might as well assume that everyone in this block is traveling at 290. Everyone in this block is traveling at 310. We just assume that. And because we're assuming that, that's why we're going to get an estimated value. And in terms of, remember, these are frequencies. We need to change the frequency to probability. Now you can see it's based on 200 trials. So to get the probability, all we have to do is do the frequency divided by 200, and that will get it for us. So this one, guys, is like it's 4, so 0.08. Actually, other way around, 4 divided by 200, so that's like 0.02 actually. So this one's 0.02, this one's 0.04 as a probability, this one is 10, so 10 over 200 is like 0.05, this one's 12, so 0.06, this one's 18, so 0.09, this one's 40, so half, that's like 20%. This one's 54, so that's 27%, 34 is 17%, 20 is 10%, and that's it. I know in my exam I double checked that it added up to 1. 2 plus 4 is 6, plus 5 is 11, plus 6 is 17, plus 9 is 26, plus 20 is 46, plus 27, 73, plus 17 is 90, plus 10 is 100. There you go. So now it's almost become a DRV. It's basically become a DRV where these are the scores and these are the probabilities. So then effectively the expected value of W is sum of all the, W values times by the corresponding probability. The W values are all the midpoints, and the probabilities we just worked out by dividing the frequency by 200. So that's 270 times 0.02 plus the next one was 290 times by 0.04 plus 310 times 0.05 plus 330 times 0.06 plus 350 times 0.09, and then there's a couple more left, plus 370 times 0.2 plus 390 and 0.27 plus 410 times 0.17, and lucky last, plus 430 times 0.1. I was quite surprised for this to come up in the exam just for 2 marks. I mean, it's a lot of work. But anyway, gives us 375.8 kilometers. That's the expected value. Okay? Now, in which company would Brianna be more likely to drive to Albany without recharging? Now, how far away was Albany? Albany was 420 kilometers away. So the probability that she can get to Albany with using the first type of car, which is a Zapra. So if she uses a Zapra, the probability that she gets to Albany was this, right? We worked that out earlier, so we're going to have to reference it. What if she uses a Spruikey? Spruikey, the variable is defined by W. What's the probability that a Spruikey will let her travel more than 420 kilometers? So 420 gets us up to like here. So then it's really just a 0.1%, like 10% chance, or a 0.1 probability, right? 0.1 is the probability. So, so therefore, probability that X is more than 420 is more than the probability that W is more than 420. So therefore, we can basically say the Zapra would be more suitable, would be more likely, Zapra would be more likely to cover the 420 kilometers to Albany without recharging. Quite easy, 2 marks. Okay, cool. All right, question 14. As a maths teacher, Mr. Ulam devised a new game that had 4 standard dice. Standard dice meaning dice like with uniform discrete random variable of 1 to 6. A player rolls all the dice. Any dice with a 1 facing up are removed. Any dice with a 1 facing up are removed. The remaining dice are rolled again. The game is finished when the player has 2 or more winning dice. Okay, so alright, the winning dice are removed, and as soon as someone collects 2 or more winning dice, as soon as someone collects 2 or more ones, we remove it. Mr. Ulam plays the game 500 times and records how many rolls it takes to win. Sometimes he's really lucky, and after 1 roll, he's already got his 2 ones, and then he can just finish the game. Okay, but sometimes he just needs to keep rolling till he has a total of 2 dice that did eventually show the 1. Alright, fine. Using the experimental data above, what's the probability of winning in exactly 2 rolls? Well, there you go. So you can see that this is 1 roll, 2 roll, 3 roll, 4 roll. So the probability that we win in exactly 2 rolls is 113. So that's pretty easy. The probability that we win in 2 rolls is 113 divided by 500, which is 0.226. Not winning in 2 or less rolls. Probability of not winning in 2 or less rolls. This is 2 or less. I could add all these up, but that seems like a significant trek. So it'll be easier just to go the other way around. So first I'll just find the probability of winning in less than or equal to 2 rolls. That's 66 plus 113 divided by 500, which is, as a decimal, 0.358 exact. We want the complement of that scenario. We want the probability of not winning in 2 or less rolls, meaning winning in, I guess, 3 or more, effectively more than 2. So 1 take 0.358 and 1 take 0.358 is 0.642. Cool. Cool. I'm just curious, by the way, what do these numbers add up to? 2 plus 5, 7, plus 4 is 11, plus 3 is 14, plus 6 is 20, 33, plus 26 is 59, plus 40, 59 plus 40 is 99, 99 plus 57 plus 57 plus 108, 99 plus 57 plus 57 plus 108. And that's 321. Is that what we got? 321 divided by 500 as a decimal was 0.642. Yep. Now, the reason why I was curious is, guys, theoretically, this could have not added up to 500, because do you guys realize that this doesn't stop? You might theoretically, possibly, you need to roll even like more times. Maybe you need to roll, so this goes up to what? 11, 12, 13. Theoretically, it's possible that you need to wait up to 14 rolls before you get your 2 ones, okay? If you're just having a very unlucky day, you just won't roll a 1. So I was thinking that what if these guys didn't even add up to the correct number? But in this case, it did. It did add up to the correct number of what we got. It did add up to a total of 321 rolls. But I was just thinking that possibly it might not have. Maybe this goes on for more and more and more possible values, and maybe you had to do the complement first. But either way, you would have got the answer. All right, state 2 reasons why the game cannot be used, modeled using a binomial distribution. Now, guys, what are the criteria for binomial distribution? There's 3 criteria for binomial distribution. The 3 criteria for using a binomial distribution is 1, that the rows are, basically the trials are independent. So that's one requirement, is the trials are independent. Another requirement is probability of success is constant. Probability of success is constant. Probability of success is constant. And another one is like, there's a fixed number of trials, to be honest, okay? There's a fixed number of trials. So those, the main two of these, and then there's 2 options that it's either this or that, okay? So these 2 are essential requirements to be using a binomial distribution. So what are 2 reasons why the game cannot be modeled? 1, we can explain that the trials are not independent, okay? The trials / rolls are not independent. And a simple example is, as the number of dice in a roll, as the number of dice in any roll depends on the previous rolls. Depends on the outcome. Maybe there's more dice, maybe there's less dice. So the number of dice in any roll depends on the outcome of previous rolls. Okay, so that's one issue, outcome of previous rolls. So we've broken one of the criteria, that it's not independent. We can explain that the probability of success is not fixed. All right, the probability of success, probability of success is not constant. E.g., if a single winning dice is removed, for example, if a single winning dice has already been removed, or die has already been removed. Alrighty, so that's another one. And then another one, guys, is like the number of rolls is not fixed, okay? That's what I was trying to tell you before, that we could keep going for infinity rolls if you're having an unlucky day. So the number of trials or rolls is not fixed, i.e., we can explain that rolls will continue until the two what's the roll? Until 2 or more winning dice are rolled. Until 2 or more winning dice are removed. And that's clearly not binomial, okay? It's clearly not binomial if you have like infinite possible number of trials, okay? You have to have a fixed number of trials. It's not like a explicit criteria to make it binomial, but it is a criteria of a binomial distribution that you have a fixed number of trials, okay? Anyway, Mr. Ulam comes up, uses the computer to simulate 10,000 games to better estimate the probability. Guys, look, it actually goes up to like 14, 15, 16. That's what I was trying to tell you before. You could have more than 13 potentially needed. You could possibly need more than 13 rolls. That's why maybe adding these would not have worked. Maybe there were like some numbers like missing, okay? So this clearly shows that sometimes you need 14 or 15 or whatnot. Well, not 16, but you need sometimes way more rolls before this happens. Okay. Anyway, to fundraise for a local charity, Mr. Ulam charges $1 for a game and pays out winnings as follows. Now be very careful whether this question is in terms of Mr. Ulam, the charity, or whether it's in terms of the player. So you can clearly see that Y is the profit. Let Y be the profit for a player who plays. Okay, so Y is for the player. A lot of people don't read the question, and sometimes they change the perspective mid-question. Alrighty, so the game is won if the game is won in 1 or 2 rolls, the player wins $2. Okay, so the player wins $2 if the game is won in 1 or 2 rolls. So then we just have to so that would mean that they actually have a profit of $1. That would mean they have a profit of $1. They already paid $1 to play the game. So they have a profit of $1, and we just have to add up these two probabilities. So if I add up, probably I should put the highest number here. So if I add up these probabilities, then the probability of 0.134 plus, just do some working out, so 0.134 plus 0.215 adds up to 0.349. So there you go, there's a 0.349 probability of that happening. Cool. If the game is won in 3 rolls, the player wins 1 in 3 rolls. Okay, well, 3 rolls is the player wins their money back. So 3 rolls is that one there. So that's got a probability of 0.208. And then we just do, well, it's a bit silly to add all the rest up. So it would be easier to just do 1 take away that. So this one is $0, and then 1 take away that. So 1 take 0.208 take 0.349 gives us 0.443. So there's a 0.443 that the player loses the $1 that they pay to play the game. Okay, cool. So calculate the expected value of Y. So the expected value and variance, and it's worth 2 marks, 2 marks. So honestly, I'd put that straight into my class pad. All right, if you don't want to put it in your class pad, you could do it manually, but there is no reason to. The expected value of Y is sum of all the Y's times by the corresponding probabilities. This times this plus this times this plus this times this. So that's that's effectively negative 0.443 plus 0 plus 0.349. Great. The expected value of Y is minus 0.094. So that's like a negative number. So I guess I write dollars equals negative $0.094. I could have put that into my list mode as well. The variance is of Y. The variance of Y is the expected value of Y squared minus the expected value of Y all squared. The expected value of Y squared is sum of all the Y squareds times by the corresponding probability, and we already worked out this number to be minus 0.094, so minus 0.094 squared. Okay, Y squared, I need a separate row with Y squared. That would be 1, 0, and still 1. Oh, interesting. So it would be positive 0.443, because this times this is now positive 0.443, still plus 0, still plus 0.349, and then minus away technically negative squared, but doesn't really make a difference. Take away 0.94 squared, and we get negative 0.783. So in terms of units, it's a bit of a weird units. It's like negative dollar squared 0.783. Okay, that's technically the units. Okay, cool. So that's the expected value and the variance. It was only worth 2 marks each. So since it was only worth 2 marks each, you could have put that straight into list mode in your class pad, and you would have got full marks. Okay. Yeah, you would have got full marks. Okay. Cool. I'll just show you how to put into list mode for those that don't know. So stats, we put the possible values here, -1, 0, 1, and then we put the corresponding probabilities. So we had a probability of 0.443. We had a probability of 0.208 for winning back nothing. And then we had a probability of 0.349. Okay. Calc, one variable, change your frequency to list 2, and there you go. You get this point -0.94, and then you get the standard deviation of 0.8849655. 8849655. 8849655. Square that, and that gives you the variance that we had earlier of 0.783. Okay, so that's if you wanted to use your class pad to do the question. Okay, cool. In the long run, now notice midway, a lot of people miss this easy 2 marks. A lot of people miss these easy 2 marks. So this is the expected value or the profit for a player. This is the expected value or profit for a player. Alrighty, but the next part is not talking about the player. The next part, it's saying, do you expect the game will be profitable for the charity? And a lot of people missed that completely. Okay, they missed. So do you expect the game will be profitable for the charity? So here's the thing. 1 mark for saying yes. So we can explain that the expected profit to the player is what? The expected profit for the player, the expected profit for the player is what we just worked out. The expected profit for player is negative $0.094. That's the expected profit for the player. So therefore, the expected profit for the charity, the expected profit for the charity is positive 0.094 per game. Alright? Alright, the expression is positive 0.094, which is more than 0, therefore profitable for the charity. Okay, a lot of people lost that easy mark because they didn't realize the question went in terms of the, they changed the perspective to in terms of charity, therefore profitable for charity. Just had to read. Alrighty, cool. That's the end of the probability for all of 2024 WACE. Well done.